So we have a good idea now on the basics of EC2 and how it can help with any compute needs, like making coffee. Well, like metaphorically making coffee. The coffee represents the whatever your instance is producing. The next thing we want to talk about is another major benefit of AWS, scalability and elasticity, or how capacity can grow and shrink based on business needs. Here is the on-prem data center dilemma. If your business is like 99% of all businesses out in the world, your customer workloads vary over time, perhaps over a simple 24-hour period, or you might have seasons where you're busy and weeks that are not in demand. If you're building out a data center, the question is, what is the right amount of hardware to purchase? If you buy for the average amount, the average usage, you won't be wasting money on average. But when the peak loads come in, you won't have the hardware to service the customers, especially during the critical moments that you expect to be making all your results. Now, if you buy for the top max load, you might have happy customers, but for most of the year, you'll have idle resources, which means your average utilization is very low. And I've seen data centers with average utilization under 10% just out of fear of missing peak demand. So how do you solve the problem on premises? Well, the truth is you can't. And here is where AWS changes the conversation entirely. What if you could provision your workload to exactly the demand every hour, every day? Well, now you have happy customers because they can always get the services they want. And you have a happy financial officer because they get the ROI your company needs. And here's how it works. Morgan is behind the counter. She's taking orders. And we have a decoupled system. Morgan isn't doing all of the work here, so we need somebody making the drinks. Looks like Rudy's up. Now, the first problem I want to solve is the idea that we plan for a disaster. There's a great quote by Werner Vogel that says, "Everything fails all the time, so plan for failure and nothing fails." Or in other words, we ask ourselves, what would happen if we lost our order-taking instance? Well, we'd be out of business until we get another person to work the line. Sorry, another instance up and running. So here is where AWS makes it really simple. Using the same programmatic method we used to create the original Morgan, we can create a second Morgan. So if one fails, we have another one already on the front line and taking orders. The customers never lose service. Well, and don't forget about the back end. Let's make our processing instances redundant as well. So that gets our regular operating capacity. We now have a highly available system with no single point of failure. And as long as the number of customers in line stays the same, we're good. But you know that's going to change, right? So let's take a look at what's going to happen when we have a rush of customers, an increase in demand.
Okay, so in terms of the scalability, right? Scaling. Scalability, there are two types, dynamic scaling and predictive scaling. In terms of, okay, so dynamic scaling responds to changing demand. Okay. Predictive scaling automatically schedules the right number of Amazon EC2 instances based on predicted demand. So as we have seen before, Amazon EC2 means Amazon Elastic compute cloud. That's what it means. Amazon EC2 means Amazon Elastic Compute Cloud. So dynamic scaling and predictive scaling. Dynamic scaling responds to changing demand, and the predictive scaling automatically schedule the right number of Amazon EC2 instances based on predicted demand.
Now, there are two ways to handle growing demands. You can scale up or scale out. Scaling up means adding more power to the machines that are running, which might make sense in a few cases, but think about it. When you have an increase in customers, a bigger instance of Morgan really can't take a customer's order any faster because that depends on the customer more than Morgan.
I'll take an espresso. Oh wait, is that organic? Make it a soy latte. Actually, I don't know. Do you just have tea?
What we need are, well, more Morgans. Customers? Oh no, looks like the processing instances are about to get overloaded. So let's scale them as well.
Obvious question is obvious. How come there are more order taker instances than order makers?
Well, in this case, the amount of work you can get done is still more than the order machines can send your way. You don't have a backlog, so no reason to add more worker instances. This is one of the great things about decoupling the system. You can end up with exactly the right amount of power or for each part of your process, rather than over-provisioning to solve a separate problem.
Coupling the system.
Okay, looks like we just cleared that rush. Now here's where AWS really makes a difference to your business. All these extra workers that are now sitting around idle, if you don't need them, send them home or stop the instances. Amazon EC2 auto-scaling adds instances based on demand and then decommissions instances when they are no longer needed. This means that every minute of the day, you always have the correct number of instances. Happy customers, happy CFO, happy architecture.
Scaling, auto scaling, yeah. Guarantee. Okay.
So we solved the scaling problem with Amazon EC2 auto scaling. But now we've got a bit of a traffic problem, don't we? Let's take a look at the situation. When customers come into the coffee shop, right now they have 3 options for which cashier to talk to place an order. And oddly enough, most of them are lining up in one line, causing an uneven distribution of customers per line, even though we have other cashiers waiting to take orders, standing around doing nothing. Customers come in and aren't sure exactly where to route their order. It would help a lot if we added a host to the situation. A host stands at the door, and when customers come into the coffee shop, they tell them which line to proceed to for placing their order. The host keeps an eye on the cashiers taking orders and counts the number of people in line each cashier is serving. Then it will direct new customers to the cashier that has the shortest line, is the least bogged down, thus allowing the lines to be even across cashiers and helping customers be served in the most efficient manner possible. The same idea applies to your AWS environment. When you have multiple EC2 instances, all running the same program to serve the same purpose, and a request comes in, how does that request know which EC2 instance to go to? How can you ensure there's an even distribution of workload across EC2 instances? So not just one is backed up while the others are idle, sitting by. You need a way to route requests to instances to process that request.
ELP.
What you need to solve this is called load balancing.
Load balance.
A load balancer is an application that takes in requests and routes them to the instances to be processed. Now, there are many off-the-shelf load balancers that work great on AWS. And if you have a favorite flavor that already does exactly what you want, then feel free to keep using it. In which case, it will be up to your operations team to install, manage, update, scale, handle failover and availability. It's doable. Odds are what you really need is just to properly distribute traffic in a high performance, cost efficient, highly available, automatically scalable system that you can just set and forget. Introducing Elastic Load Balancing. Elastic Load Balancing, or ELB, is one of the first major managed services we're going to talk about in this course. And it's engineered to address the undifferentiated heavy lifting of load balancing. To illustrate this point, I need to zoom out a bit here. To begin with, elastic load balancing is a regional construct. And we'll explain more of what that means in later videos, but the key value for you is that because it runs at the region level, rather than on individual EC2 instances, the service is automatically highly available with no additional effort on your part. ELB is automatically scalable. As your traffic grows, ELB is designed to handle the additional throughput with no change to the hourly cost.
So what ELB does is elastic load balancing. So when you have a lot of traffic coming in, and it takes the traffic and it redirects traffic to the available service. So, the more traffic you get, the system will automatically make service available. And the elastic load balancing will be able to redirect those incoming traffics. It's the same. The same model as the traffic police, right? When you go to a traffic, you got the police trying to redirect. Just a simple example, so that we don't, there's no jam, there is no blockade.
When your EC2 fleet auto scales out, as each instance comes online, the auto scaling service just lets the elastic load balancing service know that it's ready to handle the traffic, and off it goes.
This case is
once the fleet scales in, ELB first stops all new traffic and waits for the existing requests to complete, to drain out. Once they do that, then the auto scaling engine can terminate the instances without disruption to existing customers. ELB is not only used for external traffic. Let's look at the ordering tier and how it communicates with the production tier. Right now, each front-end instance is aware of each back-end instance. And if a new back-end instance comes online in this current architecture, it would have to tell every front-end instance that it can now accept traffic. This is complicated enough with just half a dozen instances. Now imagine you have potentially hundreds of instances on both tiers, each tier shifting constantly based on demand. Just keeping them networked efficiently is impossible. Well, we solve the back-end traffic chaos with an ELB as well. Because ELB is regional, it's a single URL that each front-end instance uses. Then the ELB directs traffic to the back-end that has the least outstanding requests. Now, if the back-end scales, once the new instance is ready, it just tells the ELB that it can take traffic and it gets to work. The front end doesn't know. And
okay, I just want to recap to better understand the role of the ELB, which is elastic load balancing. So the elastic load balancing can be positioned on the front end of the traffic to redirect the traffic. And also it could be placed between the systems, between the servers. So you have the ordering tier server, which goes to production tier. So there's a communication between them. in order to avoid congestion, in order to avoid load of incoming traffic, we place the ELB between the servers so that it balances, it balances the traffics. So this is the point I
Doesn't care how many back-end instances are running. This is true decoupled architecture.
decouple. Okay, this is decouple architecture. Okay, decouple architecture. Decouple or loosely coupled architecture.
There's even more that the ELB can do that we'll learn about later, but this is good enough for now. The key is choosing the right tool for the right job, which is one of the reasons AWS offers so many different services. For example, back-end communication. There are many ways to handle it, and ELB is just one method. Next, we'll talk about some other services that might work even better for some architectures.
Messaging and queuing.
Let's talk about messaging and queuing. In the coffee shop, there are cashiers taking orders from the customers and baristas making the orders. Currently, the cashier takes the order, writes it down with a pen and paper, and delivers this order to the barista. The barista then takes the paper and makes the order. When the next order comes in, the process repeats. This works great as long as both the cashier and the barista are in sync. But what would happen if the cashier took the order and turned to pass it to the barista and the barista was out on break or busy with another order? Well, that cashier is stuck until the barista is ready to take the order. And at a certain point, the order will probably be dropped so the cashier can go serve the next customer. You can see how this is a flawed process because as soon as either the cashier or barista is out of sync, the process will degrade, causing slowdowns in receiving orders and failures to complete orders at all. A much better process would be to introduce some sort of buffer or queue into the system. Instead of handing the order directly to the barista, the cashier would post the order to some sort of buffer, like an order board. This idea of placing messages into a buffer is called messaging and queuing. Just as our cashier sends orders to the barista, applications send messages to each other to communicate. If applications communicate directly, like our cashier and barista previously, this is called being tightly coupled. A hallmark trait of a tightly coupled architecture is where if a single component fails or changes, it causes issues for other components or even the whole system. For example, if we have application A and it is sending messages directly to application B, if application B has a failure and cannot accept those messages, application A will begin to see errors as well. This is a tightly coupled architecture. A more reliable architecture is loosely coupled. This is an architecture where if one component fails, it is isolated and therefore won't cause cascading failures throughout the whole system. If we coded the application to use a more
Okay, let's focus on these two phrases, right? These are very important. Tightly coupled architecture and the loosely coupled architecture. So these are extremely important. What is the tightly coupled architecture? So the tightly coupled architecture is when there is a communication between A and B, between two systems, and if one of the system fails, the other one will also fail. Okay, so that's the tightly coupled architecture. In terms of the loosely coupled architecture is when one system fails, the other will continue to work without any issues. So I wanted to focus on these two terminologies. They're very important. Tightly coupled architecture where one system fails, the other one also fails. It's a complete failure. Loosely coupled architecture, one system fails, it doesn't impact the functioning of the other systems.
Or loosely coupled architecture, it could look as follows. Just like our cashier and barista, we introduced a buffer between the two. In this case, we introduced a message queue. Messages are sent into the queue by application A, and they are processed by application B. If application B fails, application A doesn't experience any disruption. Messages being sent can still be sent to the queue and will remain there until they are eventually processed. This is loosely coupled. This is what we strive to achieve with architectures on AWS. And this brings me to two AWS services that can assist in this regard. Amazon Simple Queue Service, or SQS, and Amazon Simple Notification Service, or SNS. But before I dive into those two services, let me just order a to-go coffee on our cafe website.
So Amazon SQ service. This is for queuing. Okay. And then you have Amazon notification services. That's SNS. So for the thing that allows the loosely coupled architecture to function is the buffer. So you have to include a buffer between the application, between the system, that will allow, and basically a queuing, right? When one system receives the order and the other system, if it's not functioning, the order will go to the queue, right? And it will wait there until the other system start working. All right. So then it will process all the orders. So that's the SQS that will allow the SQS. The SQS server. Okay, hold on. Amazon Simple Queue Service. So you got Amazon Simple Queue Service and Amazon Notification System.
And Amazon Simple Notification Service, or SNS. But before I dive into those two services, let me just order a to-go coffee on our cafe website. Done. All right, well, that's great. I should get a message when that order is ready. First up, let's discuss Amazon SQS. SQS allows you to send, store, and receive messages between software components at any volume. This is without losing messages or requiring other services to be available. Think of messages as our coffee orders and the order board as an SQS queue. Messages have the person's name, coffee order, and time they ordered. The data contained within a message is called a payload, and it's protected until delivery. SQS queues are where messages are placed in a payload.
So payload is data contained within a message. Okay, that's important terminology. Payload. So the payload meaning data which is contained inside the message. In a message. So the example here is an example of payload is the queue or the buffer, right? E.g. the buffer can be called payload because inside the buffer there's a messages. Okay. Payload.
and it's protected until delivery. SQS queues are where messages are placed until they are processed, and AWS manages the underlying infrastructure for you to host those queues. These scale automatically, are reliable, and are easy to configure and use. Now, Amazon SNS is similar in that it is used to send out messages to services, but it can also send out notifications to end users. It does this in a different way, called a publish subscribe or pub sub model. This means that you can create something called an SNS topic, which is just a channel for messages to be delivered. You then configure subscribers to that topic and finally publish messages for those subscribers. In practice, that means you can send one message to a topic, which will then fan out to all the subscribers in a single go. These subscribers can also be endpoints, such as SQS queues, AWS Lambda functions, and HTTPS or HTTP webhooks. Additionally, SNS can be used to fan out notifications to end users using mobile push, SMS, and email. Taking this back to our coffee shop, we could send out a notification when a customer's order is ready. This could be a simple SMS to let them know to pick it up, or even a mobile push. Oh, in fact, it looks like my phone just received a message. Looks like my order is ready. See you soon.
Okay, we do have some quiz here. Which AWS service is the best choice for publishing messages to subscribers? So we talk about simple notification service, Amazon simple notification service. So we have to look for that one. All right, that's good. And the next one, there's not, okay, there's no next. Additional compute services.
EC2 instances are virtual machines that you can provision with minimal friction to get up and running on AWS.
So just want to drive the point home. EC2 instances, which is basically a virtual machine, virtual servers. EC2 instance, virtual server, virtual machine, it doesn't matter. Service. All right.
Yes. And EC2 is great for all sorts of different use cases, like running basic web servers to running high-performance computing clusters and everything in between. That being said, though EC2 is incredibly flexible, reliable, and scalable, depending on your use case, you might be looking at alternatives for your compute capacity. EC2 requires that you set up and manage your fleet of instances over time. When you're using EC2, you are responsible for patching your instances when new software packages come out, setting up the scaling of those instances, as well as ensuring that you've architected your solutions to be hosted in a highly available manner. This is still not as much management as you would have if you hosted these on premises, but management processes will still need to be in place. You might be wondering, what other services does AWS offer for compute that are more convenient from a management perspective? This is where the term serverless comes in. AWS offers multiple serverless compute options. Serverless means that you cannot actually see or access the underlying infrastructure or instances that are hosting your application. Instead, all the management of the underlying environment, from a provisioning, scaling, high availability, and maintenance perspective, are taken care of for you. All you need to do is focus on your application, and the rest is taken care of. AWS Lambda is one serverless compute option. Lambda is a service that allows you to upload your code into what's called a Lambda function, configure a trigger, and from there, the service waits for the trigger. When the trigger is detected, the code is automatically run in a managed environment, an environment you do not need to worry too much about because it is automatically scalable, highly available, and all of the maintenance of the environment itself is done by AWS. If you have 1 or 1,000 incoming triggers, Lambda will scale your function to meet demand. Lambda is designed to run code under 15 minutes. So this isn't for long-running processes like deep learning. It's more suited for quick processing, like a web backend handling requests or a backend.
Okay, so I just want to recap. We have serverless, what do you call it? Serverless EC2, right? So the example of serverless system is Lambda. The serverless system will basically manage your application or your code without you managing yourself, and you won't have any access to the back-end infrastructure. So that's a system of Lambda system.
and expense report processing service where each invocation takes less than 15 minutes to complete. If you aren't quite ready for serverless yet, or you need access to the underlying environment but still want efficiency and portability, you should look at AWS container services like Amazon Elastic Container Service, otherwise known as ECS, or Amazon Elastic Kubernetes Service, otherwise known as EKS. Both of these services are container orchestration tools. But before I get too far here, a container, in this case, is a Docker container. Docker is a widely used platform that uses operating system level virtualization to deliver software in containers. Now, a container is a package for your code, where you package up your application, its dependencies, as well as any configurations that it needs to run. These containers run on top of EC2 instances and run in isolation from each other, similar to how virtual machines work. But in this case, the host is an EC2 instance. When you use Docker containers on AWS, you need processes to start, stop, restart, and monitor containers running across not just one EC2 instance, but a number of them together, which is called a cluster. The process of doing these tasks is called container orchestration, and it turns out it's really hard to do on your own. Orchestration tools were created to help you manage your containers. ECS is designed to help you run your containerized applications at scale, without the hassle of managing your own container orchestration software. EKS does a similar thing, but uses different tooling and with different features. Both Amazon ECS and Amazon EKS can run on top of EC2. But if you don't want to even think about using EC2s to host your containers because you either don't need access to the underlying OS or you don't want to manage those EC2 instances, you can use a compute platform called AWS Fargate. Fargate is a serverless compute platform for ECS or EKS. That's a bit high level, and it might be confusing, so let's clear that up.
Yeah, it is.
If you are trying to host traditional applications and want full access to the underlying operating system like Linux or Windows, you are going to want to use EC2.
Correct.
If you are looking to host short-running functions, service-oriented or event-driven applications, and you don't want to manage the underlying environment at all, look into the serverless AWS Lambda. If you are looking to run Docker container-based workloads on AWS, you first need to choose your orchestration tool. Do you want to use Amazon ECS or Amazon EKS? After you choose your tool, you then need to choose your platform. Do you want to run your containers on EC2 instances that you manage, or in a serverless environment like AWS Fargate that is managed for you?
Okay.
Those are just some Do you want to run your containers on EC2 instances that you manage, or in a serverless environment like AWS Fargate that is managed for you?
Okay, so so for the to run Docker container-based workloads. So for that one, you have two options. One option is ECS, Elastic Compute Service. Right? No, I'm sorry, Elastic Container Service, or Amazon EKS, Elastic Kubernetes Service. So the Elastic Container Service, in that case, so you had a container service, and you want to use EC2. If you use EC2, you have to manage for it by yourself, because the EC2, you have to do the managing. But if you want the management to be done automatically, you can use AWS Fargate, which is going to manage for you. AWS serverless. So this is an example of serverless system, AWS Fargate.
Those are just some of your compute options with AWS, and it's not even a complete list. Check out the notes for more information on AWS compute services, as well as others that we didn't get to talk about in this video.
Sure, compute services, serverless computing, this is what.
Hey everyone, I hope you've been enjoying the course so far. We're going to do check-ins like this one after each major topic to review what you've learned. First things first, what is cloud computing and what does AWS offer? We define cloud computing as the on-demand delivery of IT resources over the internet with pay-as-you-go pricing. This means that you can make requests for IT resources like compute, networking, storage, analytics, or other types of resources, and then they are made available for you on demand. You don't pay for the resource upfront. Instead, you just provision and pay at the end of the month. AWS offers services in many categories that you use together to create your solutions. We've only covered a few services so far. You learned about Amazon EC2. With EC2, you can dynamically spin up and spin down virtual servers called EC2 instances. When you launch an EC2 instance, you choose the instance family. The instance family determines the hardware the instance runs on, and you can have instances that are built for your specific purpose. The categories are general purpose,
Which is
compute optimized, memory optimized, accelerated computing, and storage optimized. You can scale your EC2 instances either vertically by resizing the instance or horizontally by launching new instances and adding them to the pool. You can set up automated horizontal scaling using Amazon EC2 autoscaling. Once you've scaled your EC2 instances out horizontally, you need something to distribute the incoming traffic across those instances. This is where the elastic load balancer comes into play. EC2 instances have different pricing models. There is on demand, which is the most flexible and has no contract. Spot pricing, which allows you to utilize unused capacity at a discounted rate. Savings plans or reserved instances, which allow you to enter into a contract with AWS to get a discounted rate when you commit to a certain level of usage. And savings plans, which apply to AWS Lambda and AWS Fargate, as well as EC2 instances. We also covered messaging services. There is Amazon Simple Queue Service, or SQS. This service allows you to decouple system components. Messages remain in the queue until they are either consumed or deleted. Amazon Simple Notification Service, or SNS, is used for sending messages like emails, text messages, push notifications, or even HTTP requests. Once a message is published, it is sent to all of these subscribers. You also learned that AWS has different types of compute services beyond just virtual servers like EC2. There are container services like Amazon Elastic Container Service, or ECS. And there's Amazon Elastic Kubernetes Service, or EKS, both of which are container orchestration tools. You can use these tools with EC2 instances, but if you don't want to manage that, you don't need to. You can use AWS Fargate, which allows you to run your containers on top of a serverless compute platform. Then there is AWS Lambda, which allows you to just upload your code and configure it to run based on triggers. And you only get charged for when the code is actually running. No containers, no virtual machines, just code and configuration. Hopefully that sums it up. Catch you in the next one.
Okay, so let's take some quizzes. You want to use an Amazon EC2 instance for a batch processing workload, group processing, right? What would be the best Amazon EC2 instance type to use? Batch processing meaning you have multiple data processing, at the same time, multiple, right? Because it comes out as a group. What would be the best Amazon EC2 instance type to use? General purpose, memory optimized, compute optimized, storage optimized. So in this case, we need something that will be able to handle a lot of data coming in. So that's going to be compute optimized. Okay. And what are the contract length options for Amazon EC2 reserve instances? The contract lengths are 1 to 3 years for reserve instances. You have a workload that will run for a total of 6 months and can withstand interruptions. What will be the most cost-effective Amazon EC2 purchasing option? You have a workload that will run for a total of 6 months and can withstand interruptions. What would be the most cost-effective, cost-efficient Amazon EC2 purchasing option? Reserve instances, spot instances, dedicated instances, on-demand instances. So I believe this is going to be spot instance. Spot instances. Which process is an example of elastic load balancing? elastic load balancing, ensuring that no single Amazon EC2 instance has to carry the full workload. Removing unneeded Amazon EC2 instances when demand is low, adding a second Amazon EC2 instance during an online resource backlog sale, automatically adjusting the number of Amazon EC2 instances to meet demand. So that's going to be the first one. The elastic load balancing which is will direct traffic so that one Amazon EC2 instance doesn't carry all the workload. So it takes the traffic and directs to the available EC2 instance. EC2 instance here is the virtual server. You want to deploy and manage containerized application. Which service should you use? You want to deploy and manage containerized application. Okay, so not AWS Lambda, that's a serverless system, not Amazon SNS, not Amazon SQS, Amazon Elastic Kubernetes Service, Amazon EKS, Amazon Elastic Kubernetes Service. So that's going to be the last one. Okay, what do you got? The next model. What the interesting. All right, so what do we have here?
I want to talk to you about high availability. Say you want to grab a cup of coffee at the cafe, but today is not just a normal day in our city. Today, there is a parade coming to march down our street in celebration of all of the wonderful cloud migrations that have been successful. This parade is going to march right in front of our shop. This is great because who doesn't love to look at floats and balloons and have someone throw candy at them from the street? But this is also bad because while the parade is coming down the street, our customers who are driving to come get coffee will be diverted and won't be able to stop by the shop. This will drive sales down and also make customers unhappy. Luckily for us, we thought ahead. We thought long ago, what would happen if for some reason our customers couldn't make it into the shop temporarily? Like if there was a parade, or if there's a flood, or some other event that blocks us from getting into the shop. Well, no matter the reason, we need to be highly available for our customers. So I'll let you in on a secret. This isn't our coffee shop's only location. The cafe is actually a chain, and we have locations all around the city. That way, if a parade comes down the street, or if there was a power outage on our block, no worries. Customers can still get their coffee by visiting one of our shops just a few blocks away. We still make money and they get their coffee, all is well. AWS has done a similar thing with how the AWS global infrastructure is set up. It's not good enough to have one giant data center where all of the resources are. If something were to happen to that data center, like a power outage or a natural disaster, everyone's applications would go down all at once. You need high availability and fault tolerance. Turns out it's not even good enough to have two giant data centers. Instead, AWS operates in all sorts of different areas around the world called regions. We're going to talk about this in depth in upcoming videos. In the meantime, I'm going to sit here and relax because I know my business is highly available, regardless of any parades blocking the street.